Thank you, Fred. Our next up is Joanna Joyner. She has worked for over 20 years on the Aura satellite. She was first a deputy project scientist and then the US science team leader for the ozone monitoring instrument. She's currently the flight project scientist for the GeoXO mission with NOAA and the instrument scientist for the atmospheric composition instrument that will be one of the 5 instruments for GeoXO. She's worked on a huge array of different satellite retrieval algorithms, and today she's going to talk about advanced high spatial resolution nitrogen dioxide OCI product and potential applications for it. So welcome to the stage, Joanna Joyner. And I will switch to your talk here now. And good to go. Thank you.
Thanks. So I have a couple of mantras here. One is, if you build a good instrument, you're going to do way more than you thought you could. And the second one is, one person's noise is another person's career. So with that, we were I was attending a PACE science team meeting a couple of years ago, and nitrogen dioxide came up because it interferes with the ocean. And it was asked whether we could actually get nitrogen dioxide from PACE. So my team and I looked into it, and we thought we could. And now we have the real data. So sometimes these things work out not as well as you thought they did, or they would, and sometimes they work out better. And that was actually the case for this. So first, I'd like to get into the motivation. If you don't know about nitrogen dioxide, or NO2, it has sources that are both natural and anthropogenic. Natural sources are from wildfires, soil, and lightning, and anthropogenic is from any type of burning of fossil fuels or biomass. It's a pollutant. It's an EPA criteria pollutant. It has adverse health effects. And it's also a climate agent. It contributes to the formation of aerosols and tropospheric ozone, and both of those are also criteria pollutants. So it's a very important molecule for chemistry, atmospheric chemistry. And as I mentioned, it impacts the ocean color algorithms. So we wanted to know if we could get nitrogen dioxide from PACE, and if so, then it can potentially provide some value-added data for the air quality and atmospheric chemistry communities, and so I'll give you some examples. And here you see NO2, an annual average from the TROPE-OMI instrument. And so you can see, basically, you can see civilization here. You can see all the places where fossil fuels are burned and fires. Okay, so just to give you a little background on the heritage instruments for trace gases like NO2 have typically had higher spectral resolution than what we have from PACE. So in the more or less in order of magnitude, so in the 0.5 nanometer range, and because of that, there are only so many photons to go around. You have to trade off spectral and spatial, so those instruments tend to have lower spatial resolution. The highest spatial resolution is the NASA TEMPO instrument, which was launched a little bit before PACE, and that's in geostationary orbit. But the really interesting thing from PACE would be if we could do it getting down to that 1 kilometer resolution. So this shows you the NO2 absorption cross sections, and you can see the overall curvy shape of that. I'm going to see if I can point here. Can you all see that? Yeah. And then there are these little wiggles. And so the trace gas, the heritage instruments are going for these big wiggles in this window. This gray window here is what we use with the OMI instrument. But when you get to PACE resolution, that's the red curve. The wiggles are way down, but they're still there. And when we looked into it and we delved into machine learning, what we found is that it's actually these wiggles could provide the information that we need to get NO2 out of PACE. Actually, this large shape really is difficult to to get any information from, and we found that the ultraviolet wavelengths out in here were not providing too much information. But with PACE, we have the advantage of being able to use this wide spectral range from the UV into the vis, and we have these wiggles here. And our trace gas instruments, most of them only go to 500 nanometers, so we have this extra 100 nanometers here, which is interesting because there's less Rayleigh scattering in these wavelengths than in the blue, where the heritage instruments are. And so that's going to help us get down to the surface where we really want that information on how much NO2 is down here where we're breathing it. So our approach was to try to train on data from the tropomi instrument, so not to develop a physically based spectral fitting algorithm, but go straight from tropomi to PACE. And we didn't know how well that was going to work, but we gave it a try, and you'll see. So we're using machine learning here, and the basic approach, first we do this decomposition of the spectra into principal components, and we find that that makes it easier for the algorithm to converge and for the machine learning to get its coefficients. And we're training again on tropomi, which is got lower spatial resolution, and so we're still working on the best way to do that, but basically what we're doing is we are bidding the PACE up to the tropomi spatial resolution and training a network, and then we're applying it down at the 1 kilometer. And we found that worked a little better than kind of a nearest neighbor approach. Okay, so some results, and I am really excited about this. This is groundbreaking resolution that we're getting out of PACE. So here, what you're looking at, the top row is PACE on 3 different days, and then you have a weekend day, Sunday, and then Monday you see the NO2 from the traffic is much more, and Tuesday, for whatever reason, a little bit less. And then you see what it looks like to tropomi. So we're really getting these features now. You can actually see NO2 on highways. You can see it very nicely stacking up against the mountains here. And on the bottom is tempo. And so tempo is a little bit better resolution than tropomi, but not quite as good as PACE. And you do see that tempo is a little bit higher. I'll get into that in a minute. But this looks spectacular to me. A couple of more examples. This is Riyadh, which is an interesting place where the wind blows in all different directions. And you can see what that does. And in Riyadh, you have a lot of individual sources that you can see. Maybe you can't see it on here, but cement factories, and power plants. So on the top, you have tropomi on the left, PACE on the right, and 2 different days, top and bottom, with the wind blowing in different directions. And it looks very, very different. But with the PACE data now, you can really start to see some of these individual plumes, individual power plants that in the tropomi data, they're kind of, some of them get mixed up. And with this, we'll be able to do a better job estimating emissions from these different smaller sources that are close together. Another example, Ohio River Valley. Here we have 2 cities, Cincinnati and Louisville. On the top, those are the bigger areas of pollution, but a bunch of power plants in between in here. And again, with the tropomi data, these kind of merge together, and with PACE, you can see the individual plumes a little bit better. You can see the difference between a windy day on the top and a calm day on the bottom. You start to really see these sources distinctly, particularly this one down here. Which is a power plant, and that is distinct from the rest of the city here. So this is, again, super excited about this. Here's another example in Detroit. So you have a lot of vehicle emissions from Detroit and power and different industrial plants. And you can really see some examples of sharper features in the PACE data. And again, this is going to be able to be used to better define emissions in cities. Okay, and another example in the Middle East with a lot of different sources here, isolated power plants, cement factories, desalination plant, tropomi on the left, PACE on the right, and you can see the better defined plumes and the difference that you get with the different winds. You can really see this south wind, these distinct plumes very nicely in the PACE data. And see these, even these small sources, you can start to see the plumes very nicely. And these here, again, power plant, cement factory, and these are really getting blurred out in the tropomi data, and you get a very nice plume at the 1 kilometer spatial resolution. And finally, Southeast Texas, a bunch of, you have a couple of big cities here, and Houston and San Antonio, and then you have the smaller cities, Austin, Waco, Killeen, and College Station. You can start to see these much better in the PACE data, and again, actually see the highway traffic here very nicely. You know, of course, what we always do with these data, we do average them in time. We can do this spatial oversampling. We can get to even higher resolutions than our instruments. So we ought to be able to get to sub-kilometer when we start averaging the PACE data together in time. So potential applications are improved spatially resolved emissions estimates. You have better resolution when you're looking at human exposure. For health, improved ocean color retrievals, improved chemistry transport modeling for air quality, and spatial downscaling of the tempo hourly measurements. So starting to use the high temporal of tempo with the higher spatial from PACE. And so those things are very complementary. So this stuff is hot off the press, and I want to acknowledge my colleague, Zach Fastnacht, who did all the work here. He did a tremendous job to get this data out so quickly. We are fine-tuning the algorithm. We're conducting validation. We've looked at the data compared with, I see that last slide got, it's out of order. But this is our validation comparisons against Pandora ground-based measurements. So on the left, you have the PACE at 1.5 kilometer, then you have PACE at 4.5 and tropomi at 4.5. And you see that we're getting very similar results between PACE and tropomi. And you might say, well, should PACE be better? But I want to point out that with our machine learning, we are not bringing in any other data other than the spectra and the solar zenith angle. The tropomi algorithm is very complex. It brings in profile information, information about the surface reflectance, aerosol, cloud, you know, the height and amounts, and we are essentially getting information from the spectra. So being able to use all that spectral range is actually helping us get information about the profile and allowing us to reproduce a similar quality as tropomi without all that complexity. So that just shows you the power of what's in the spectra. So we're going to continue. We've got some aircraft data to look at. and a little bit more fine tuning, then we hope to get this into the paste processing system so we can get it out to people and start using it and expanding what we're doing. Here we just focused on land. We want to do ocean, and we've been focusing on clear sky. We think we might actually even be able to do good retrievals in partly cloudy conditions. So thank you very much. No atmosphere people here?
Okay. I just wanted to terrestrial question, but it will be really lovely to overlay the estimates of air pollution distribution with the vegetation maps that Fred was showing and really understand what is causing it and what are the cause and effect relationships. And because it's from the same sensor at the same time, this is really possible. So it's marvelous, it's great. And so are you going in that direction?
Yes.
Excellent.
And I should mention that NO2 is not the only atmospheric component that we can do. Zach has actually done ozone as well. So that's also what we hope to do.
And what about CO2? Can you do?
CO2 is pretty tough.
Okay.
Yeah,
Well,
that one's really hard.
It's okay. Thanks.
I understand you're using machine learning to enhance the and refine the basically where the nitrogen dioxide is, but could it also be used to predict acid rainfall? Because currently it's only being predicted 12 to 24 hours in advance. Do you think it could go even earlier than that with this?
I'm going to leave that to the next generation of grad students to be able to use this data in creative ways to try to get at things like acid rain. Yes. Probably that's not what we're going to do. We're going to just try to make the best product we can so that all the other smart people can do great things with it.
Thank you.
Thank you for the great talk. I have a quick question. I see in your slides you're using a lot of vertical column nitrogen dioxide. Is there a reason you're focusing on vertical column instead of the tropospheric?
Yes, it's easier. So to get to the tropospheric column, then we would need to estimate the stratosphere. So there are different ways of doing that, and our group does have a lot of experience doing that. We just haven't done it yet. This is where we want to get to first. Also for the ocean community, what they're going to want is actually the total column. So we wanted to see how well we could do that. Just again, directly, we're training on tropomi, which is has different geometries. So we weren't even sure that we could do this problem that well, direct, sort of transfer from one instrument that's has different geometries to another. But that worked. But I think we can definitely get to tropospheric columns. We just haven't done it yet.
Okay, thank you.